Types of chemical bonds. A chemical bond is simply an attractive force that holds atoms together. There are three major types of chemical bonds that we're going to talk about. And some of this is review from Chem 1, but we're going to go a little bit deeper into it. When we have an ionic bond generally involves metals from the left side of the periodic table interacting with non-metals from the right-hand side of the table, and we end up with a complete transfer of electrons. You have atoms that want to lose electrons to form ions, which would be our metals, and you have the non-metals that want to gain electrons to form ions. So you're going to have these positive and negative ions that are formed, and that positive-negative electrostatic attraction is what holds that compound together. Now remember, ionic compounds do not have molecules. They have a crystal lattice structure. So you can think about how strongly this is held together in terms of crystal lattice energy. Now look at this crystal lattice energy equation. And it's a variation of Coulomb's law. It says that the energy, the crystal lattice energy, and again, by this energy, we're talking about the crystal lattice energy, is equal to K as some constant, a proportionality constant. It's different for each substance, and we don't really worry about the K part. What we're worried about are the charges, Q1 and Q2, and the distance between the ion centers, D. So just in general, look at what this equation is saying. It's saying that if the charges are bigger, there's a bigger force of attraction. That makes sense. If the distance between the ion centers is larger, then you're going to have a lower, you're going to have a lower crystal lattice energy, and therefore they're not going to be as attracted as strongly. So keep those two principles in mind. The bigger the charge, the more the attraction. The bigger the distance between them, however, the less the attraction. A negative crystal lattice energy, as it says here, indicates that the compound is lower in energy than the individual atoms. It has given off energy to form, so it favors the formation of that compound. So let's talk about the formation of a compound containing potassium and barium. Could we make a barium potasside or a potassium baride compound? Well, hopefully that sounds as weird to you as it is, because look at what you would be doing. As it says here, if you think about this equation, and I do want you to refer back to Coulomb's law, that's very important in all of our discussions about this. If we look at what this equation is telling us, forming an ionic bond between K plus and Ba2 plus would result in a positive crystal lattice structure energy, and that would be unfavorable for the formation of a compound. Remember, negative crystal lattice energy favors the formation of a compound. So as soon as we get a positive energy in this situation, it is not going to favor the formation of that compound. The next question, which would have a higher melting point, sodium chloride or potassium chloride? The first thing that you should do is just to analyze. If we're looking for a higher melting point, what are we looking for in our compound? Are we looking for something that has a stronger attractive force between the ions or a weaker one? Well, if we want a higher melting point, what that means is it's going to take a lot more energy to break apart that compound, to break apart that lattice structure. So we're talking about a strong attractive force. So we're talking about a large crystal lattice energy. So look at what we would need. If we want a large crystal lattice energy, one of two things would need to happen. We would either need to have a large charge, or we would need to have a small distance between ion centers to get that large energy. So those are our two choices, a large charge, larger charge, or a smaller distance. Now, if you look at both of these, you'll notice that both of them are +1, -1 ion compounds. What does that mean? It means charge is going to make no difference for these two. So charge is not going to play a part in this. Size, however, does. So since we're going to be looking at size, we've got to look for the smaller distance between ion centers. And if you look at your periodic table, you'll see that sodium in the third energy level is going to be significantly smaller than potassium, which has its valence electrons in the fourth energy level. That means sodium is smaller than potassium, so sodium chloride is going to have a stronger attractive force. And so it's going to have a higher melting point. It's going to take more energy to break down that ionic bond. So what about being soluble in water? Which one would be more soluble in water? Once again, you have to think about whether we're talking about here a large crystal lattice energy or a low crystal lattice energy, because are we wanting something that's attracted very strongly or weakly? If we want it to be soluble in water, then we're going to want a weak attractive force. So we're going to want a small ionization energy, I said ionization energy, a small lattice structure energy, small lattice energy. So more soluble means we want it to be able to break down easily. Now, if we want a small crystal lattice energy, then we want one of two things. We want either a small charge, we want that to be small, or we want this to be large. We've already established that for potassium chloride and sodium chloride, the charges are the same, so that's not going to help us out any, so we're looking at distance. This time we're looking at the larger distance between ion centers, which is going to be our larger atom, our larger ion, potassium. So since potassium is larger than sodium, potassium is going to be held less strongly, as it says here, less strongly attracted to the chlorine, and therefore would have a greater solubility because it's easier for water to break apart those ionic bonds. So it's all about lattice structure, and it's all about lattice energy when we're describing these things. Now, be careful. This only works for ionic compounds. Don't try to use this equation for a covalent compound. Covalent compounds work on a whole different level, and that has to do with intermolecular attractive forces, which we'll talk about later. This is all about ionic compounds. So our next question, which would have the higher melting point, sodium chloride or magnesium oxide? Now, higher melting point, analyze it again. Higher melting point means we want it to be attracted strongly because we want it to take a lot of energy to melt it. So this is a large lattice structure or lattice energy. And if we're looking for a large lattice energy, we're either looking for a large charge or we're looking for a small distance between ion centers. Charge, generally we think of charge trumping size. So if we look at these two substances, sodium chloride and magnesium oxide, we look at charge first, and we see that sodium is a +1, chlorine's a -1, magnesium's +2, oxygen -2. So in this case, magnesium oxide has a larger charge difference. According to Coulomb's law, that's going to result in a larger lattice energy, more negative lattice energy, and therefore magnesium oxide would have a larger or higher melting point. It's going to take more energy to break down those ionic bonds. So high melting point, we always have to refer it back to crystal lattice energy. Always have to refer it back to that. Now, we can also do this with size, because if you look at the difference between sodium chloride and magnesium oxide, sodium is bigger than magnesium and chlorine is bigger than oxygen. So size is going to work in the same way this time. Since magnesium and oxygen are both smaller, they are going to have a smaller distance between their ion centers and therefore going to be attracted more strongly to each other as well. So, now, as far as the solubility, remember, solubility is the opposite of melting point. Solubility, we want a weak attraction, so we want there to be a low lattice energy in the compound. So low energy is what we're looking for, a weak attractive force. So if we're looking for weak or low energy, then we're looking for charge to be small and for the distance to be large. Smaller the ion charge between the two ions that are being joined together in that crystal lattice. The larger that, or excuse me, the smaller that charge, the smaller the lattice energy and the less strongly they're attracted. And look again up there. If you remember what we just wrote, sodium plus 1, chlorine minus 1, magnesium plus 2, oxygen minus 2. So there's your answer. Sodium chloride is going to be held less strongly. It's got a lower charge. It's also bigger, remember. So Coulomb's law says that both of those are going to lead to a lower energy and therefore a more soluble compound. It's going to be easier for water to break it up. Now, characteristics of ionic compounds. They're solids with high melting points. That crystal lattice structure, that is a very strong electrostatic force of attraction between every single ion in that crystal lattice. So it's going to be very high melting points, like it says, typically greater than 400 degrees. Since they have those charges, they're soluble. They tend to be soluble in polar solvents. Water being the most common polar solvent. So they tend to be soluble at least slightly, but in those polar solvents, but generally quite soluble. Most are insoluble in nonpolar solvents. Nonpolar solvents have no charges themselves to break apart those ions, so they tend to repel those solvents. So now, as far as conducting electricity, there's something that you need to remember, and that's mobile charged particles, MCP, mobile charged particles. That's what you've got to have in order to conduct electricity. If you don't have mobile charged particles, then you don't get electricity conducted. Now think about an ionic compound. It has tons and tons of charged particles. It's made up of ions. But when it is solid, think about it. When it's solid, it's not going to be able to conduct electricity. Tons of charged particles, but it's not mobile. It can't move. So think about it then. Why do molten ionic compounds and aqueous solutions of ionic compounds conduct electricity really well? It's because they have not just the charged particles, but they're able to move. So you have to remember that ionic compounds, solids do not conduct electricity, but if they're molten or aqueous, they do. They tend to be brittle and shatter when they're hammered. If you look back, I guess it's back on this other page, if you look back here and you think about hammering this lattice structure, keep in mind that all of these blue and yellow little spheres are positives and negatives attracted to each other. Now let's say we hammer this and we get those layers off just a little bit so that instead of being positive, negative, positive, negative, positive, negative, all of a sudden we've got positives lining up with positives and negatives lining up with negatives. And that's going to create a repulsive situation, and those are going to break apart. You do that on enough layers and it's going to completely shatter that crystal lattice structure. So that's why they tend to be brittle. I think I went too far. The formulas are usually given in simplest ratio of the elements. Think about why. It's in a crystal lattice structure. You can't divide it into molecules. There's no such thing as molecules for these. So they are in the simplest ratio, 1:1 or 2:1 or 1:2. That's the way that they come up with their formulas. Now, covalent bonds, if you want to go back and listen to the notes over ionic, metallic, and covalent bonding, you can from Chem 1. It's back in Unit 9 of Chem 1. But covalent bonding involves the sharing of electrons, and it happens between two atoms that are generally nonmetals. And these atoms are going to be the ones that have electronegativity values that are not very far apart. So when that electronegativity, remember, is the tug-of-war force, that force of the electron, of those atoms pulling on that shared pair of electrons. And if the force is not very strong, they're not going to be able to rip any electrons away from the other atom. So what's going to happen is they're going to have to share the electrons. And we'll review that whole process of how those molecules look in the next couple of days. So with those shared electrons, we don't get electrons being ripped away. What we get is, we don't get these charged ions. And since we don't have charged particles in there, what you've got between the molecules, we'll just say that these are just covalent molecules. I won't give them a name, but let's say all of these are just covalent molecules. The thing that's holding them together is not strong electrostatic attractive forces. The molecules themselves are being held together like the arms or the head on a person. But between those molecules, we've got fairly weak intermolecular attractive forces. Again, we'll talk about those on a later day, but those weak intermolecular attractive forces are all that's holding those molecules together. They're not charged. They might be polar. They might have some slight charges on them, but they're not going to have those full-fledged charges like an ionic compound would have. So they're not going to have that high melting point. They're going to be pretty low melting points because all you have to do is give it enough energy to break down these intermolecular attractive forces. So when you boil water, you're not separating the oxygens from the hydrogens. You're just separating water molecules from each other, and those water molecules are attracted by intermolecular attractive forces, but they're not nearly as strong as the attractive forces between the hydrogens and the oxygens. So low melting points. They tend to be insoluble in polar solvents because they don't have any charges. If they don't have any charges, you're not going to be able to split them up by something that has charges. Now, nonpolar solvents tend to be able to dissolve them just by sliding around between the molecules. Liquid and molten compounds, they don't conduct electricity pretty much at all. Neither do the aqueous solutions. They're poor conductors as well. Even if they're moving, even if they're molten or aqueous, there's no charges. You have to have, remember, mobile charged particles. They have to be both mobile and charged. If they're not both, they won't conduct electricity. So they can be as mobile as they want to be moving around, but if there's no charge on them, they're not going to conduct electricity. And since covalent compounds do not have a charge, they're not going to conduct electricity. The polar ones, you can get them to conduct electricity very weakly, but it's still not great. The formulas are given in true ratios because when you have a covalent compound, you have individual discrete molecules. And those molecules, you get the actual molecular formula for those molecules, H2O for water in this case. Now the last kind of bond we want to talk about is the metallic bond. The metallic bond is formed between identical metal atoms. And what happens is we have these cations. For instance, if this were a silver bracelet, there are these silver cations here, and what's happened is that their valence electrons have been stripped off of those silver atoms, and the valence electrons are free to move throughout that piece of metal. Those valence electrons are often called a sea of electrons because of that. And this sea of electrons is going to give them specific characteristics. They usually are crystalline solids, but they have a range of melting points, and often it's dependent upon the number of valence electrons they have. They're very good conductors of electricity when they're solid even, because think about it, mobile charged particles, even when this bar of silver is a solid, that sea of electron is They're still free to move throughout that bar of silver. They're malleable and ductile. They're malleable and ductile because if you hammer it, stretch it, as long as you're not really abrupt with it, you can get a piece of metal to snap, but as long as you're just stretching and pulling and hammering, and stretching and doing it fairly slowly, you're giving that sea of electrons time to go in and just kind of cushion those cations and keep them from coming in contact. If you do it too abruptly, you can get those silver cations to come, closer to each other, and if they do, they're going to repel and they're going to shatter. But as long as you have that done fairly slowly, you're going to give that piece of metal time to readjust electron-wise, and you're going to be able to stretch it into thin wires, hammer it into sheets, all of that stuff. They're also very shiny. So